Now we are getting into something which is called the phases of matter, and the phases of matter are very simple, straightforward: gas, liquid, solid. So you know about the three phases, but what we have not talked about so far is why and how these three phases occur. And can you predict what a phase of a substance is going to be? So if I give you any compound, can you tell me that it's going to be a solid, liquid, or a gas? So in this chapter, some of those things will become clear, and hopefully you should be able to predict those kind of things in this chapter, or after learning about this chapter. The key thing about determining whether something is going to be a gas, liquid, or a solid is actually intermolecular forces. So I've divided this chapter up into two or three different presentations. So the first one here, this focuses primarily on just the intermolecular forces, so you can understand what those are. They're very key in understanding the phases of matter. Okay, so just as a review, let's look at the different phases of matter and the interconversions between those matters and what they're called. So the three phases are solid, liquid, and gas, and you can convert everything into everything else. And the type of the intermolecular force will determine what the phase is. So that's where we're going eventually. However, I just want to mention a few keywords here to you, okay, so that you remember them. So we have the three phases here: solid, liquid, and gas. All right, and you can see the solid are very compact. The molecules are close together. In case of liquids, they are not as close together, okay, but they take the shape of the container. Solids, you can actually knock them into a shape, particular shape, but liquids will take the shape of the container. Gas molecules will take the shape of the container, but they're also not close together at all right, so gases have very different properties, as you know from your GenChem 1. However, let's look at the different phases that we're talking about and how to convert from one to the other. When you go from a solid to a liquid, that is called melting. And these are all terms that we use all the time, but I just want to emphasize them again so that you remember them. Going from liquid to gas is vaporization. Gas to liquid is called condensation. I would prefer it if we don't use liquefaction. Try to use condensation more than liquefaction. Liquefaction is used a lot more in industry than in normal terms. Okay, and so try to use condensation. Going from a liquid state to a solid state is called freezing. Okay, just like normal, we call that. Um, Sublimation is the conversion between a solid to a gas. All right, so there is the liquid phase is bypassed, okay, in this one, and the gas can go back to the solid in deposition. Okay, you have done all of these things one way or another, whether you have melted ice in order to give liquid, or whether you have boiled water to go from liquid to a gas state. And then if you remember, in one of your labs, you actually sublimed iodine, and that was sublimation process, going solid to gas, and then deposition. It was depositing back into a solid state. This is a very nice chart, but the way I teach it is I usually put that in a triangle form. Okay, and so I learn it much better this way. And so I would suggest that you go ahead and fill in all the sides over here. So for example, solid to liquid will be melting, liquid to gas will be evaporation, gas to solid would be deposition, and then you can take the arrows on the other side, so solid to gas is sublimation, and so on. So you can color code it also and all that. So I left this up to you, but I learn a little bit better using a triangle. Okay, so if you want to use it, it's there for you. So let's talk about intermolecular forces now. All right, intermolecular forces are forces that exist between molecules. So it's not intramolecular. Intramolecular would be within, which is actually what we call, when we have a polar bond, that would be intramolecular, but intermolecular is between two molecules. All right, so we have plenty of molecules. It's the forces between them. The nature of the force and how much the forces will cause a substance to be a solid, liquid, or gas. So the higher the force, then it takes a higher energy to separate the molecules, obviously. Okay, so if two molecules are held together very closely by a force, it obviously will take a lot of energy to separate them out. So then the higher the intermolecular force, the higher the vapor pressure, which means the higher the boiling point or the melting point. Okay, so which means that it's taking a lot of energy to separate those molecules out. So just imagine the molecules going on from a liquid state to a vapor state. In a liquid state, they're all together in a container, but in a gas state, they're far apart, which means that the intermolecular forces are pretty much non-existent. Okay, but in a liquid state, the intermolecular forces are holding them together. So the higher the intermolecular forces, the higher amount of energy is going to take to break them apart, which means that something is going to have a higher boiling point. So that's kind of where we're going with all of this. And it seems like it should be a simple concept, but when you start applying it, sometimes we are not able to, which is why I'm taking my time to explain all of this. The higher the intermolecular forces, the more chances of a substance to be a solid versus a liquid versus a gas, which means that the highest intermolecular forces are in solids. That is why they're held together so closely, and then the intermolecular forces in gases are pretty much nil. They're not there. If they had intermolecular forces, they would not be a gas. They would start condensing, which is really what happens when you have fog. So when you have all of this water vapor in the atmosphere, it's all apart, all the gas molecules, all the water molecules are floating around, and suddenly when the temperature goes down and the water molecules start getting closer together, then you start getting fog, you start getting condensation, because now suddenly the intermolecular forces have increased. Okay, so that's kind of what goes on. So, and when you have solid, of course, the intermolecular forces are at their highest. One of the other ways to tell if you have good intermolecular forces is, of course, by dipole moment. The higher the dipole moment, the higher the intermolecular force. Okay, and remember we talked about dipole moment back in GenChem 1 when we were talking about the shapes of molecules and electronegativity of atoms and then polar bonds and all of that good stuff. Okay, and so you need to kind of review all of that, okay, in order to understand intermolecular forces. So here are some examples of some boiling points and dipole moment of some molecules that have similar molecular mass. It's really important that you compare apples to apples and not apples to oranges. You can compare apples to oranges too, which we will, okay, a little bit over here, but at least they should have something similar in them. Okay, so what is similar over here is their molecular mass, okay, which means they weigh about the same. So here's propane, and if you look at propane, the only atoms that are in there are carbon and hydrogen. The dipole moment is almost nothing, okay, when compared to something like acetonitrile, which is 2.9 dipole moment. So if the dipole moment is high, then the boiling point will be high as well, okay, which is 82 versus minus 42 for propane. Propane at a boiling point of minus 42 really is actually a gas, okay, it's not even a liquid at that point. Then we're looking at ether over here. So ether has an oxygen in the middle. Oxygen, as you know from your GenChem 1, is a little bit of an electronegative element. And so because of that, there is a little bit of dipole moment. And because of that dipole moment, the boiling point has changed. Okay, so boiling point changed about 20 degrees Celsius. So that is kind of what this table indicates over here, that as you change the structure of the molecule, then the dipole moment changes and then the boiling point will also change. So what kind of intermolecular forces are interplaying here within these molecules? That's where we're going to, okay? But right now this table is about dipole moment and boiling points, okay? So it gives you a little bit of an idea how this works. Here are the types of intermolecular forces that you will encounter in chemistry, and this is not in just general chemistry. Once you get to organic chemistry, you will encounter them here, and then biochemistry again, you will encounter the same three intermolecular forces. So that's the nice thing. The bad thing is you will encounter them over and over again, so you might as well learn it, okay, because these are a very important part of chemistry. So I've arranged them according to their strength. So London forces, dispersion forces are the weakest of the forces, of the intermolecular forces, and these forces result from instantaneous dipoles and induced dipoles. And don't worry, I will explain everything in the next slide. Okay, dipole-dipole interactions are when you have polar molecules. And remember again, we learned about polar molecules back in GenChem 1 when we learned about the structure of molecules, the 3D structure, and then we determine the dipole forces, okay, or dipole moment of a molecule. So you need to know the 3D structure of a molecule in order to figure out dipole-dipole. And then there is hydrogen bonding, which is one of the strongest forces that we have for intermolecular force. And this is a very, very specific kind of a force. It is a force in polar molecules that contain a hydrogen atom in addition, okay, which means that the hydrogen atom is actually bonded to a highly electronegative element. And the highly electronegative element can be nitrogen, oxygen, or fluorine. Okay, these are the three most electronegative elements on the periodic table. Chlorine has high electronegativity, but chlorine does not promote hydrogen bonding. Chlorine just promotes dipole forces. Okay, so this is very, very specific in the sense that hydrogen has to be bonded to nitrogen, oxygen, or fluorine in order to show hydrogen bonding. Okay, it's not just hydrogen bonded to a hydrogen and then another molecule where you have nitrogen. No, the hydrogen has to be bonded to nitrogen, oxygen, or fluorine. Okay, all right, we'll get to it again later on when I'm going through it more. This little table here actually shows you how much force is involved in any of these intermolecular forces. So for example, the van der Waals force, the London forces, dispersion forces. The approximate energy used to break those forces is 0.1 to 10 kilojoules per mole versus hydrogen bonding, which is 10 to 40. Okay, so really hydrogen bonding is a lot stronger than the van der Waals forces. Okay, very, very, very stronger. So that's the amount of energy it requires. In case of chemical bonding, when we have two kinds of bonding, where we have ionic and covalent, the approximate energy can range, okay, from anywhere from 100 to 1,000. Now remember, when we have ionic or covalent bonding, this is a bonding between the two atoms. Okay, this is different because now you're sharing or you're giving or taking electrons. Whereas in case of intermolecular forces, this is between two molecules, so the interactions are a lot weaker, and that is why they can be broken easily. To break a chemical bond, a covalent bond or an ionic bond takes a lot more energy. In fact, ionic bonds are one of the strongest bonds out there. Okay, covalent bonds, not so strong. Um, the variation here is from 100 to 1,000, which doesn't tell you anything, but covalent will be more towards the 100 and ionic would be more towards the 1,000. Okay, so it takes a lot of energy to break ionic. But intermolecular forces, it doesn't take a whole lot, okay, of energy to break them, which means you can separate molecules out, which is how we go from one phase to another phase. So let's look at the London forces first, which is also called dispersion forces. These are also called the van der Waals forces. You can call them all sorts of things. Okay, so anyhow, we'll call them London forces to begin with. Most of the time, they will exist only in nonpolar molecules. Okay, nonpolar molecules meaning that there is no difference in the electronegativity. So molecules like diatomic molecules, oxygen, nitrogen, chlorine, fluorine, all of these, they don't have any difference in electronegativity. So you will see that there, or you will also find this in case of noble gases. Noble gases don't bind to anything, okay? However, you can see some sort of London forces in noble gases, okay? Because when you're talking about something like helium, it's a very small size, but then by the time you come down to krypton and all, then there's really large size of an atom. So then you start seeing the dispersion force in there, okay? And so you can also have these kind of forces in molecules that have heteroatoms. So for example, something like methane, okay, which is CH4. So CH4 is not homonuclear, which means it doesn't have the same kind of atoms. It's heteronuclear. However, it does have a little bit polarity, but not too much. Okay, so when you subtract the two electronegativities, carbon and hydrogen, the molecule turns out to be nonpolar. Okay, and so you will see the London forces in all sorts of nonpolar molecules. Here is what happens, okay, when you have a large atom, okay, when you have a really large atom like neon or iodine, bromine, any of those atoms which get larger in size, then it generates what we call an induced dipole. Okay, so what happens then is that you have, say, one atom of neon. Okay, so when it approaches another atom of neon, then there is an internal dipole. Okay, and what happens in that case is that because the atom is so large, the negative charge tends to localize at one place and the positive tends to localize in another place. So which means that you start having these delta positives and delta negatives within an atom. So when you have a large atom, this is what happens. If you have a small atom like hydrogen, fluorine, helium, you cannot see that charge dispersion because the volume is not that much of an atom. So if the volume is not that much, there is nowhere for the electrons and protons to separate out. However, with large atoms, this is possible because there is so much room, there is so much space that electrons and protons will start to separate out. And once they do that, and when they approach another atom, the negative side of one atom will attract the positive side of another one. And so this creates what we call an induced dipole. So, which means that they by themselves really have no polarity until another atom comes by, and then you get this induced dipole. Okay, and so this is what we mean by induced dipole. And this is a very typical property that occurs when you have large atoms or very large molecules. Okay, so when you have large molecules, meaning when you have so many atoms in there. So for example, when we're talking about propane, before it had 3 carbon atoms, but when you talk about something like octane, which is 8 carbons, it is very different. So in the 3 carbon atoms, which was propane, it is actually a gas, but when you get to C8, it is a liquid, okay, which is the petrol that you put in your car. So there is so much difference between C3 and C8, okay? So the molecule gets larger, and so the dispersion forces increase because of this induced dipole, okay, in there. So that's what London forces are. By themselves, they have no polarity, nothing else, okay, going on for them. Let's look at another example for the dipole forces, and that is in the halogens, okay, group number 7, where we have fluorine, chlorine, bromine, and iodine. So we have 4 elements over here to talk about. And here is the molar mass given for all the 4 elements. And of course, the molar mass increases as you go from fluorine to iodine. Iodine is humongous. It's got plenty of protons and neutrons. And here are the states that are at room temperature for these molecules. So fluorine and chlorine are both gases. Bromine is a liquid and iodine is a solid. This is a very neat group, okay, to talk about because of all of these differences that it has. Fluorine and chlorine are gases because fluorine and chlorine are very small atoms. They're not very large, so which means that there is no induced dipole in them. Okay, remember fluorine by itself is going to be a nonpolar, which means or a nonpolar molecule because fluorine is attached to fluorine or bonded to fluorine, and so there is no dipole moment. Okay, so we're talking about just diatomic molecules, homonuclear diatomic molecules. When you come to bromine now, okay, it turns into a liquid, which means that there is some intermolecular force going on here. The only intermolecular force possible is obviously the London force, and that is because of the induced dipole. So when you come to bromine, the size is very large for bromine. And so once the atomic size is very large, you can have that dispersion going on where you have the positives on one side and negatives on one side. So when another molecule of bromine comes along, then those 2 dispersion forces start to interplay, and then you start having intermolecular forces. So then you have bromine as a liquid. This induced dipole is so much for iodine that it turns into a solid because iodine is larger than bromine, which means that it has more electrons and more protons to disperse, so it has a stronger induced dipole interaction. Okay, and so it becomes a solid. So it's really neat group to talk about. Here's the property in case of a quantification for it. So here are the boiling points. Boiling point of fluorine is very low, and the boiling point of iodine obviously then will be very high because it's a solid. So it's very neat, okay, how the induced dipole works for something as simple as halogen diatomic molecule. Now a little bit back to again to carbon and hydrogens, which are also called hydrocarbons. And this particular example details a little bit about branching in molecules. We've talked about C3, C8. I mentioned it to you before, where C3 is propane, carbon 3 structure would be propane and it was a gas, and C8 structure would be a liquid, okay, because C8 is a much larger molecule, so there's induced dipole going on in there. However, there is a difference in a straight chain molecule versus a branching molecule. So here we have carbon, 5 carbons arranged in a chain, a straight chain. The boiling point of this compound is 36 degrees centigrade. Now we take 1 carbon and then we move it to a branching. Okay, so when you create a branching of that, so which means we still have 5 carbons. Now the branching causes the boiling point to change. It's lowered now from 36 to 28. Now we take another carbon atom and move it around and give it a little bit more branching, and the boiling point goes down from 28 to 9.5. So you can see that as the branching is increasing, then the boiling point is also decreasing. If the boiling point is decreasing, it must be that the intermolecular forces are decreasing. So how does this work? Okay, so again, let's look at the London forces, because the carbon-hydrogen bond is nonpolar. So if it's nonpolar, that's the only force we have to talk about, London forces. When you have pentane by itself, it has not a significant dipole moment. However, because it's a huge molecule, it can have an induced dipole. So when another molecule of pentane comes around the straight chain, it will start interacting with it through the induced dipole. Because this is a straight chain, it has a larger surface area, so which means that the interactions between the two molecules is through a larger surface area. As you increase the branching, the surface area of the molecule decreases, so which means that if another molecule comes around, there is really not much space between them to interact. In a straight chain, you have a larger surface area to interact. In branching, you don't have that much space to interact. So if the interaction is less, then you have a lower boiling point. If you have more interaction, you have a higher boiling point. It's as simple as that. So that's how branching works for intermolecular forces. So London forces are not as simple as just saying if there is no dipole, there is no force, or there is less. No, there are other factors here too. Okay, so the size of the atom, and then the branching, okay, of the molecule, and of course the size of the molecule as well. Now let's look at dipole-dipole forces. Dipole-dipole forces are a lot easier to deal with. The only thing you have to be careful about in dipole-dipole forces is the structure of the molecule. Okay, that's the only thing you have to be careful about. When you have dipole-dipole forces, the molecules will have some sort of a dipole moment. If a molecule does not have a dipole moment, then you have to throw it in the category of dispersion forces, okay, or London forces. But if a molecule has dipole forces, then this is where we will talk about it. Okay, so how do you determine if something is going to have a dipole moment? Well, first you draw the structure, okay, the Lewis structure of the molecule. Then you determine the shape of the molecule. Once you know the shape of the molecule, then you figure out the dipole moment. How? By determining the electronegativity, okay, of the two atoms or the three atoms that may be connected. So if you cannot do the two things, which means that if you cannot draw the Lewis structure and you don't know the shape of the molecule, well, then you don't know the dipole moment, okay. And so make sure that you know the Lewis structure of molecules as well as the shape of the molecule. Some molecules may have heteroatoms or may have polar bonds, but because of the shape of it, they may not be actually polar. Okay, they may not have a dipole moment. Classic example is carbon dioxide. Okay, so look through your notes again and see that carbon dioxide, even though the CO bond is very polar, it itself as a molecule has zero dipole moment because the structure is linear, okay, in it. Okay, so then the higher the dipole moment, the higher the boiling point, all right, of it, because the higher the intermolecular forces. So I'll bring this table back again. We just talked about it about 2 slides ago. And here now you can see that, okay, again, that the higher the dipole moment, the higher the boiling point. CH3, CH2, CH3, nothing here. There's not even an atom with a higher electronegativity. So it has nothing going for it except for dispersion forces. When you look at dimethyl ether, this molecule here, just pretend that this CH3 and this CH3 is not there and you have H and H over here. So even if you pretend for that, then you will remember that the shape of this molecule is actually bent. It's not a linear molecule. If it was a linear molecule, it will not have a dipole moment. But because this is not a linear molecule, the oxygen here has 2 lone pair of electrons on it. So because this is bent, it has a dipole moment, and therefore the boiling point changed from minus 42 to minus 25. Okay, minus 42 was for propane, which has absolutely no dipole moment. Then we come to methyl chloride, which carbon is a tetrahedral atom. So in the carbon, which is tetrahedral, you have 3 hydrogens and 1 chlorine. So of course that results in a dipole moment. So you have a 1.9 dipole moment, and the boiling point is similar to the dimethyl ether because yes, both of them have some dipole moment. Once you start getting into acetaldehyde and acetonitrile, the dipole moment increases, and so does then the boiling point, okay, of all of this. So once you have dipole forces in there, then of course you'll have higher intermolecular forces. Dipole forces have higher intermolecular forces than London forces. Now for the last intermolecular force, which is hydrogen bonding. Hydrogen bonding is a type of a dipole-dipole interaction, okay, that is for sure, but it's a very specific intermolecular force. It's a very specific dipole-dipole interaction because it is between hydrogen that is bonded to fluorine, oxygen, or nitrogen, FON, okay, or NOF, if you look at it the other way. Anyhow, so for example, molecules like water, hydrogen fluoride, ammonia, all of these ones are going to display some sort of hydrogen bonding because you have hydrogen attached to oxygen, here hydrogen attached to fluorine, and hydrogen bonded to nitrogen or attached to nitrogen. So the interaction that you end up getting is something like this. Now, hydrogen bonding is actually almost as strong as a covalent force in some cases. It's very strong bond, intermolecular force. By the way, the hydrogen bonding, it's called bonding, but it really is an intermolecular force, okay? So don't get confused. Hydrogen bonding is not the bond between oxygen and hydrogen. It is still an intermolecular force between two molecules, okay? So the blue lines that you see here, those are the intermolecular forces. So anyhow, this is kind of what the interaction would look like for water. So again, just to mention this, hydrogen fluoride will have hydrogen bonding, but not HCl. Okay, the chlorine here is not so electronegative in order for it to have hydrogen bonding. So here is what happens when you have hydrogen bonding going on. This is a nice little graph of elements from the same group. Okay, so this is the oxygen group, group number 6. So here we have water, which is H2O, hydrogen bonded to oxygen, hydrogen bonded to sulfur. Look at that, boom. The boiling point went down so much, okay, right away. Then the boiling point starts going up, okay, from selenium and then tellurium. Can you think about why the boiling point is going up over here after coming down? I'll give you 10 seconds. If you thought dispersion forces, you are absolutely right, okay? Because as you're going from sulfur to selenium to tellurium, then the size of the atom is increasing. If the size of the atom is increasing, the dispersion forces are increasing. So now you have intermolecular forces that are increasing this way. But between oxygen and sulfur, look at the drop here, okay? It is unbelievable. And that is because oxygen is a highly electronegative element and sulfur is not. As you come down the group, electronegativity decreases. The most important thing about hydrogen bonding that I feel you should know for now and for later also is that this is what holds the proteins and DNAs together. Okay, in our body, we are held together by hydrogen bonding. Okay, so in case of proteins, where you have a whole bunch of carbons and oxygens and nitrogens, actually, I should mention carbons because carbon is just a backbone. Okay, but you do have nitrogens and oxygens. All of those proteins are held together by all of these hydrogen bonding interactions. If the hydrogen bonding was not there, we would not have the protein structures that we do, okay, like this. They would not have the specific folding and specific structures that they do. And the same thing goes for DNA. DNA is what we call a double helical structure, okay, because it's like two strings, okay, like a spring going in, but it's two springs going together, wrapped around together. And the two springs are actually held together only by a hydrogen bond. It takes a lot of energy to break these bonds. Remember, we were talking in the previous chapter in thermochemistry about how the energies are used in the body. Well, one of the major source of energy used in the body is replication of DNA. Okay, and so once new cells are made, you have to make new DNA. And so one of the uses of the energy is to break these hydrogen bonds in order to replicate the DNA. So hydrogen bonding actually plays a great role in the 3D structure of our biomolecules. And then we have one more interaction. I didn't mention it before, but I'm going to mention it now. It's called the ion-dipole interaction. And the ion-dipole interaction is not really considered to be an intermolecular force. Okay, otherwise I would have mentioned it before. It's just an interaction because you don't see them together. The way you will see it is when you start mixing things together. Okay, you will not find it within something. So, for example, water will just have hydrogen bonding. It will not have ion dipole interaction. However, as soon as you put sodium chloride in water, now you will have hydrogen bonding as well as the ion dipole interaction because the ions are coming from sodium chloride. Okay, the reason sodium chloride dissolves in water is of course twofold. One of course is the property of sodium, as in all the salts of sodium will dissolve in water, and the other is of course the fact that sodium and water, they have similar kind of interactions. When you have ions, ions means you have cations and anions. When you have a dipole means that you have a partial positive and a partial negative. So the partial positive and partial negative can now start interacting with the cations and the anions. And because of that, you end up getting solubility. Okay, and so you can have weak interactions or you can have strong interactions depending on the size of the atom. So sodium ion is bigger than magnesium ion. So magnesium ion has a better interaction with water than sodium does. Okay, I'm not going to be asking you about whether sodium is better than magnesium. I want you to know that if you have sodium chloride dissolved in water, then the interaction that is playing there is actually an ion dipole interaction or ion hydrogen bonding interaction. What kind of interaction is taking place? So this is really a very helpful part when you talk about solubility of molecules. When you try to dissolve water in ethanol, okay, or water in hexane, water in octane, will it dissolve? So you look at the structure of those two molecules and then figure out if they have similar intermolecular forces. If they have similar intermolecular forces, they will dissolve. So that is like one of the properties of intermolecular forces. I think I'm getting a little bit ahead, but anyhow, this is what I'm getting at. Okay, so I'm not going to be asking you about magnesium ions and sodium ions specifically. I will be asking you what is the interaction, okay, between a sodium ion and water molecule. So here is an example for intermolecular forces. So it says the question is, what are the intermolecular forces that you expect for these molecules? So you look at each of the molecules and then go on from there. So O2, for example, is a nonpolar molecule. If it's a nonpolar molecule, the only force there is the London force. London force, you can call it van der Waals force, that is fine. I would not call it dispersion, okay? You can use dispersion only when you're talking about large atoms. When you're talking about small atoms, I would prefer if you use van der Waals and London forces. Okay, all right. Then we have something like H2O2. So as soon as you get to H2O2, now we have polar bonds. And as soon as you have polar bonds, you're going to have dipole-dipole forces. You're also going to have hydrogen bonding in there because now you have a bond that where you have hydrogen bonded to oxygen. So you will also see some hydrogen bonding going on. CH3Br here, it's a slightly polar molecules because bromine does have some sort of electronegativity. However, not so much. Okay, so you will have some dipole force, but the major force here would be the London force because bromine is so huge that it will cause some sort of dispersion force, or because of its size, you will have London forces. Okay, but it's not very polar. One of the things I want you to be careful of, because this is going to happen to you when you start doing problems, is when textbooks answer these questions, they will answer London forces for every single molecule. So if they were talking about hydrogen peroxide also, they will say that you have London forces in there. I would prefer if you don't use London forces for everything, because everything is going to have London forces, because every molecule is capable of having one way or another a little bit of charge dispersion. Okay, I would prefer it if you use London forces primarily for nonpolar molecules. That will help you differentiate between the intermolecular forces. If you start using London forces everywhere, then you cannot differentiate between molecules, okay, or the intermolecular forces. So please be careful. Do not use London forces for every single thing. London forces are used when you have nonpolar molecules or huge molecules, okay, which don't have that much of intermolecular force. So please limit it to that. So your key concepts in this case is change of phases that I would like you to know. I will ask you, just little multiple choice questions about what those processes are called, like evaporation, sublimation, and so on. And then obviously all the intermolecular forces. Okay, and so I will ask you whether you can predict the phase of a substance based on the force, because remember, the higher the force, the more likelihood that it is going to be a liquid or a solid. The less the force, then more likely it's going to be a gas. Okay, so you should be able to do that.